sum, because integration is defined through sums, Riemann sums. Okay, but it's like an elongated S kind of. Okay, that's the integral sign. All right. 5.1. All right. In chapter 3 and in chapter 4, we talked about derivatives. Now we have antiderivatives. All right. Antiderivatives. That's the last time I'm going to write that word. From now on, ADs. Okay. And basically, antiderivatives correspond to indefinite integrals. That's the term I use more often. And indefinite integrals. Indefinite integrals. All right. And yes, we will see definite integrals later on. That's going to be way after the test. All right. Okay, let's start with ADs. Let's start with antiderivatives. Okay. All right. Okay, let's begin with f of x equals x squared. I just write x squared here. All right. Y equals x squared. F of x equals x squared. All right. This way, we're going to take derivatives. All right. Well, if f of x is x squared, what is f prime of x going to be?
2x.
What's the derivative of x squared? 2x, please, 2x. The derivative is 2x. All right. And of course, if you graph that, that's a line. Right? Okay, you can graph derivative functions, that's fine. All right. Okay. But here's the thing, though. We're going to reverse this process. Okay, we're going to ask, you're going to be given 2x. And it's like the Jeopardy question. It's like an inverse question. Whose derivative is 2x? Now, x squared is one answer, but is it the only one? No. Give me another one. How about f or g of x, whatever, equals what? What else has a derivative of 2x?
Squared minus?
Yeah, x squared plus minus a constant, right? For example, x squared plus 1. X squared plus 1. You agree that the derivative of x squared plus 1 is 2x plus 0, right? Same derivative, right? We can do x squared minus pi, right? H of x equals x squared minus pi. The derivative is 2x. Bottom line, you agree that if we have x squared plus c, where c is any arbitrary real constant. Okay, you agree that the derivative of x squared plus c, where c is any arbitrary, it's like a random constant, the derivative will be 2x, right? Okay, so these are all antiderivatives. Okay, these are all examples of antiderivatives for this guy. These are all ADs. All these guys here. These are all ADs. Right. All right. So what are we going to say here? Given. Now actually we're going to kind of flip around the notation here. Given that little f of x equals 2x. Now I know that this guy was f prime of x over here, but the idea is that on a test you're given this 2x. All right, little f of x equals 2x. That's the guy we're looking at. We're now asking whose derivative is he? Okay, that's going to be an integration process. All right. Then, okay, now for antiderivatives we use capital F of x. It's kind of like, little f of x, right? His son is his derivative, f prime of x. His dad is capital F of x, an antiderivative. Then capital F of x, okay, can take on the form x squared plus c, where c is any arbitrary constant. All right? And this gives all, and in fact, this gives all the antiderivatives of little f of x. Okay, all of them.
If we don't put c, we get it wrong, right?
That's correct.
Okay.
That's correct. Ah. Well, maybe a minus 1. Maybe, you get nothing. But I mean, sometimes you have really hard problems. It'd be very mean of me to say, haha, no plus c, no points. I'll take off a point. Depends on the problem. Depends on the problem. Right? So the deal is that, okay, given a function, if it has a derivative, right, the derivative These give all the antiderivatives for little f of x. Maybe you have to simplify. Right? Okay. And of course, these all have the property that, okay, well, the derivative of capital F of x is little f of x. Right? What is an antiderivative? An antiderivative has the property that when you take his derivative, you get the guy we're given. Right? So your goal is to look for guys whose derivative is the guy you're given. Right? Look for guys whose derivative is the guy you're given. All right. In a way, this defines what an antiderivative is. Right? Okay, on some appropriate interval. All right. Question so far. Question so far. Is there an efficient way to describe this relationship? Yes, there is, and we use that symbol to do it. Okay, so an indefinite integral represents a family of antiderivatives. All right, issue B. What is an indefinite integral? All right, so the anatomy. Okay, this guy here, this is called an integral sign. A lot of people say it's like S for sum. Okay, this is the integral sign. Okay, you see calculus books without its cover. Right? All right, that's the integral sign. Then you put 2x. Right? That's the rule for the function you're given. The function rule you're given. All right. So this here is going to be little f of x. Right? We normally think of the guy we're given as little f of x. This is called the integrand. This is the integrand. Just like, you know when you take the square root of something, what's inside is called a radicand. This guy is the integrand. He's inside the integral expression. All right. Now remember that when we took derivatives, right, you know, it was good to write down things like dy dx or d sub x, right? So d sub x, d sub t, d sub theta, right? You should indicate the variable that's your independent variable. Okay. So we'll put here dx. Okay. And this indicates that x is the variable of integration. Okay, and you must write this. Okay, you never give an integral expression where you omit this. You always have a d something, whether it's dx, dt, d theta, whatever. Later on in Calc 3, you're going to have double and triple integrals. You're going to have things like dx, dy, dz in order. Okay. All right. Yeah.
You ever do like the reverse of implicit differentiation integrals?
The reverse of implicit.
Like, because we went from the main function to the derivative.
You are right that, well, in Calc 3, you're going to be integrating with both x and y. So in that sense, you can be dealing with more than one variable. Right, in Calc 3 though, not so much in this class, but yeah, yeah.
I still don't get it.
Oh, okay, now you know how, if I go d sub x of x squared is 2x, this indicates that we're differentiating with respect to x. Okay, so if you agree that we should have the x here, you agree that we should have the dx here. It indicates the variable, the independent variable. What's the run? What variable corresponds to runs? Okay, sometimes it's t, sometimes it's theta, right? Okay. So that's now this is like a 1-point question on the test. What is the indefinite integral of 2x dx? The answer is a family of antiderivatives. Okay, remind me, whose derivative? Wait, question?
Yes.
Okay.
So that's not d times x. That's a derivative.
No, it's not d times x. This is notation. It's differential notation. It is kind of related to that differential stuff we did earlier. It's like a change in x. Okay, we'll talk more about this after the test. Like later weeks. Whose derivative is 2x? X squared, don't forget, plus c. Okay, this is called the constant of integration, and you need it. Again, it's like -1. Depends on the problem. It's going to be like -1 if you forget it. Constant of integration. Okay, and it represents an arbitrary real number. Bear in mind, sometimes you put plus d. You can put plus d, plus happy face, whatever. Just as a reminder, little x squared, all right, this is capital F of x. This is an antiderivative of little f of x. So that's the anatomy. The integral of 2x, this is called the integrand, with respect to x, right? Just like over here, differentiating with respect to x. I'm going to stop that out, right? Here we're integrating with respect to x. Again, later on in Calc 3, you're going to really appreciate this notation. I know here it seems obvious, but I mean, come on, this looked obvious too, but it's good to indicate what that variable is, right? Okay. This indicates the variable of integration. We do need this thing there, all right? Equals, okay, x squared, that's an antiderivative, plus c. All right. This is called evaluating. Yeah.
It's the whole function x squared plus c, big F of x.
Okay, now the
Or
idea
just
is
x
that
squared.
there are many possibilities for big F of x. Okay, x
Yeah.
squared, x squared plus 1, plus 2, plus pi, minus pi. So it's a whole family of antiderivatives. Yeah. So
But I
I'll
mean, so
indicate
would
that.
we be wrong if we put big F of x equals x squared plus c?
There's a family of antiderivatives. Sorry, what was that?
So would we be wrong if we put big F of x equals x squared plus c? Would that be wrong?
What you're doing is you're giving me. What you're doing is you're that's okay. You're evaluating that integral. You're just doing it in a different format.
Okay.
I mean, if you put on the next line, big F of x equals x squared plus c, box that in, fine, I'll take that. Yeah, you're evaluating, right?
Yeah.
So to go here, okay, we're evaluating this integral. Just like here, we evaluated the derivative. Here, we're evaluating the integral. All right. So what's the general format? What are you going to be doing in Chapter 5? So in Chapter 5, you're basically be doing a whole bunch of these. You get the integral of little f of x dx. You get a problem of that form. Equals, it's kind of like what I was saying. Okay, so what do you have to find? You have to find an AD. What's an AD? You have to find an
Big F.
the big F, antiderivative, big F of x, and don't forget your plus c. And in fact, you know, for any value, any real number you put for c, that also counts as a candidate for big F of x.
That makes it more
That's a
clear.
possibility. Okay. So big F of x, that normally corresponds to the most basic antiderivative with no constant terms.
Yeah, so the c is just taking into account that there could be something else extra there. It doesn't have to be, but there could be.
The plus c is necessary. It indicates that if you add any real
Yeah, the
number,
possibility that something
you
else
get
could be there,
you
but
get
it's
an
not.
appropriate antiderivative. You must put the plus c.
Yeah.
Okay. Or plus d or whatever. Yeah. All right. Okay. So that's what you do. This. Yes. This. All right. So this is what you're going to be doing. All right. Good. Problem is, how do you find that capital F? All right. Okay, so let's look at some basic rules. All right. Well, if you know your derivatives, you should know your integrals. All right. Basic rules. All right. Although, oddly enough, these very first couple of examples, they're the ones that mess people up. Well, for example, what's the derivative of x? It's 1. Dx is 1. A lot of people forget that. All right. The derivative of x with respect to x is 1. Okay. So, what can we say as a result? How can we invert it? By the way, this is like an inverting, except that's not 1 to 1 because of the plus c. All right. We can say that the integral of 1 with respect to x is, and you know, we asked the question, whose derivative is 1 with respect to x? Right? It's going to be x plus c. Over here, plus c. Okay. By the way, if that's a t, it's t plus c. If that's a theta, it's theta plus c. Okay. So be consistent with the variable of integration. All right. And by the way, very often, if the integrand is 1, we don't even bother writing it. So we usually just write it as integral dx. If the integrand is 1, we just ignore it. Okay. Bear in mind, that's if the integrand is 1. Okay. Don't just say, oh, haha, I'll just ignore this guy. What if it's 1? All right. What's the derivative of 3x with respect to x?
1/3 x cubed. JK.
X to the third.
X. What's the slope?
3.
Slope. Slope is 3. Right? See, like I said, you can differentiate x to the 100th, you can't differentiate 3x. All right. Okay. The derivative of 3x is the slope. It is 3. Okay. Plus c? No, it's a derivative. It's a derivative. Remember, plus c on integrals, not derivatives. Know the difference. By the way, on the final, okay, a good test to see who passes the class and who doesn't. Do you know the difference between taking a derivative and taking an integral? I'm not kidding. All right.
Right now.
Okay. Therefore, the integral of 3 dx is 3x plus c. Okay, write that for the integral. And by the way, you can check these things, right? So if you're not sure, how can you check it? Take 3x, take the derivative, right? Okay, you can check this. All right, the derivative of 3x is 3. Of course, the derivative of a constant is 0. So basically, the derivative of c is 0. Okay, and the fact that it's arbitrary, don't let that freak you out. Okay, so you can differentiate to check. Remember that, you can differentiate to check. Sometimes it's kind of inconvenient though. All right, so those are basic rules. All right, and like I said, sometimes these are the ones that mess people up. Okay, the power rule is easy for people because you get used to it. All right, what about the power rule for integration? Well, if you know the power rule for differentiation, it should make sense. All right, power rule for integration. But of course, we're going to start with the power rule for differentiation. All right, the derivative of x to the 4th. Now, I'm sure you know this. What's the derivative of x to the 4th? 4x cubed. All right. Now, as a result, what can we say? What is this as an integral statement? It's kind of like with exponentials and logs. How can we rewrite this thing? All right. The integral of 4x cubed dx, all right, is going to be x to the 4th. Don't forget. Plus c. In fact, when you get an indefinite integral problem, the first thing you might want to do is put a plus c, like on the bottom right corner. Okay. Okay. If I see a plus c in there, like bottom right corner, I'll take it. Plus c. You rub your plus c. Okay. So as soon as you remove that integral sign, put a plus c, or plus d, or whatever. Right? Okay. But then you might be going. So what's the integral of x cubed itself? Well, let's answer this question. Okay. Really, let's answer this question. Whose derivative is plain old x cubed? If the derivative of x to the 4th is 4x cubed, what do I do to this so that the derivative is just x cubed, not 4x cubed? What do you want to put here? 1/4. You agree? Because if you have 1/4 x to the 4th, what happens? You apply the power rule for derivatives. 4 comes down. This goes bye-bye, right? X to the 3rd. Yeah. You see? So you have the reciprocal, basically, right? Okay. 1/4 x to the 4th. The derivative of 1/4 x to the 4th is x cubed. All right. Another way of writing this is x to the 4th over 4, right? X to the 4th over 4. So how can I write this? Oh, any questions about that? The derivative of x to the 4th over 4 is x to the 3rd. Because remember, when you differentiate, 4 comes down, kills him. That becomes 3. All right. Okay. All right. So what does that mean? What's the integral of plain old x cubed dx? All right. It's not x to the 4th. It's going to be x to the 4th over 4 plus c. All right. And this hints at the general rule. What is the general power rule? All right. What is the integral of x to the n dx? Okay. So, well, what do? We take the exponent. Now before, when we differentiated, we subtracted 1. What do we do here? We add 1. So we have x to the n plus 1. Okay. And then you divide by that new exponent. Okay. So basically, you add 1. All right. And then you copy this down over here. Okay. So remember, when you took a derivative, what did you do? The exponent came down, and you subtracted 1 over here. Now we're kind of inverting the process, right? Now we're adding 1 on top, and then dividing by that new guy. All right, so it really is inverting. Remember, when you invert something, you're inverting the steps in reverse order. Okay, here, you smack down, smack down, subtract 1. Here, you start by adding 1, and then you bring this guy down here by dividing. All right. Okay, so here you're multiplying, here you're dividing. Okay, question. This is okay as long as, okay, if n is not, there's one value for n that won't work here. Well, negative 1, yeah. If n is not negative 1. All right. But if n is any real number, and that includes the square root of 3, includes pi, right? Any real number, except negative 1, this works.
And you need plus C.
And plus C, yeah. Okay. And you need plus C, all right, over there. All right, all right. Now this kind of, it makes us a little sad that n equals negative 1 is excluded, all right? The case of n equals negative 1, we're going to see that in chapter 7. You're going to have to wait about a month for that, sorry. Okay? Which kind of makes us sad because what is this guy? Integral of x to the negative 1 dx. It's kind of sad that we don't know how to integrate him. What is x to the negative 1? It's 1 over x. Okay, so it's kind of ironic that we can integrate 1 over x squared, 1 over x cubed, but we can't integrate 1 over x yet. That's chapter 7. In case you're curious, you don't have to know this now, but you're going to have to know it in about a month. Do you know what this is? Remember this guy? That's the natural law of the absolute x plus c. That's chapter 7. Okay, but I know some of you are, tears are coming to your eyes now, but we're going to, okay, we're not going to see ln again until chapter 7. Okay. Although I will tell you, one reason why we need this, we're going to integrate guys like tangent of x by using these kinds of rules. All right. Okay, so n equals negative 1 we're going to cover later. All right. Speaking of which, I just mentioned some trig, right? So we know some trig rules. You know 6 rules for differentiating trig functions. That means we have 6 rules for integrating trig functions. All right. Now I'm going to need, I'm going to need all this space. So, all right. All right. Basic trig rules. All right. Now, folks, does this mean that you need to know 6 brand new rules? Actually, no. In fact, I would actually discourage you from trying to memorize the 6 integration rules in the sense that it's easier to remember your differentiation rules. So you should already know these, right? Know the 6 derivative rules and know how to reverse them, kind of invert them. Okay, that's the way to do it. So as an example, okay, I'll do a block here, block there, like I go. All right. Now you should know this stuff. All right, come on, folks. What's the derivative with respect to x? Yeah, derivative sine of x is what? Cosine of x. Plus c? Plus c? No, we're taking a derivative. Know the difference. Okay, you don't put plus c when you're taking a derivative, unless you see a cx or something. Okay. Now leave a blank here. I'll put 2 columns here. Leave a blank here. Okay, let's go to the integration rules. Okay, so because of that, what can we say? The integral of what is what? The integral of cosine of x dx is what? Sine of x. Don't forget your plus c. All right. Again, some people like to put parentheses here to emphasize these are functions. I think that's overkill, unless this is something more complicated than x. Okay. Where is this? Right. All right. Now, be careful. What's the derivative of cosine of x? Right, that's the opposite of sine of x, or negative sine of x. All right. Okay. Now, I'm going to write this line up here, actually. You can see it. All right. That means that the integral of negative sine of x dx is cosine of x plus c. All right. But then, what is the integral of plain old sine of x dx? All right. Well, if cosine of x is an antiderivative for him, what do you think an antiderivative for him is? Negative, or the opposite of cosine of x. And you might say, do we need minus c? Well, that's okay, but you know what? We can put plus c still, because the opposite of an arbitrary constant is still an arbitrary constant. So you don't need minus c. Plus c is still okay. All right. The integral of sine x dx is negative cosine x plus c. But again, folks, I don't recommend that you actually memorize that in the sense that it's easier to remember this rule than to know how to go backwards. Basically, there's a sign flip. Okay, know when you go from here to here, there's a sign flip. Okay, likewise, from here to here, there are sign flips. There's sign flips here. Okay, so if there is a negative here, there's not one here. If there isn't one here, there is one here. Okay, so in this column, we're going to have sign flips. Okay, that's the way to look at it.
So it's the same for the integral of cosine x dx, right? If it's negative cosine x, then it'll be just negative sine x.
Yeah, that's right. Negative cosine, right? Negative cosine x would be negative sine x plus or minus c. Yeah.
So that's negative sin x?
Yeah. If this is negative, this is negative. Meaning, okay, if this is negative, this is negative. Okay, if there's a negative sign here, there's a negative sign there. Meaning there's no sign flip. That's the deal. There's no sign flip here. There is a sign flip there. Think in terms of sign flips.
Only corresponding to sine, right? Or any other.
Well, hold on. Are you going to talk about tangent? That's later.
Well, I was, no,
Go ahead.
if the trigonometric function has a sign flip when you're taking a derivative, it is the only time that the sign flips, right?
Well, yeah, because if you get a sign flip in the derivative, you get a sign flip in the integral. Yeah.
All right.
Yeah. So these guys here are going to flip sign. Therefore, these guys here are also going to flip sign. All right. And when I say that, I mean I'm referring to the presence of that negative sign. Okay, that's what I mean. All right. Over here, the derivative of I think I do tangent x next. Yeah. Okay. Tangent x. The derivative of tangent of x. What's this? Secant squared x. Therefore, this is straightforward. The integral of secant squared x dx. Well, whose derivative is he? Tangent x plus c. All right. Now you might be asking, so what's the integral of plain old secant x dx? Guess what? That's chapter 7. We won't be able to do that until chapter 7. It's going to involve a log. Okay, but secant squared x, this is actually easier. Secant squared x is actually easier. It's a base derivative. Over here, just watch your signs. The derivative of cotangent of x. Okay, and for many of you, this helps to figure out this. What's the derivative of cotangent x?
Negative cosecant.
Negative cosecant squared x. Yeah. Notice again there's a sign flip. Over here, so what's the integral of, I'm just going to say cosecant squared x, all right? What's the integral of cosecant squared x? Yeah. Negative cotangent x plus c. Okay. In fact, some people put a c in front. That's okay. All right. Questions? So again, memorize these and know how to invert these statements. Okay, it's not one-to-one, but know how to invert these statements. All right. You can see how, if you were to have like 12 flashcards, including these, that would get very confusing. I think this would actually confuse people if you tried to memorize these on their own. Just know these cold and be able to invert them. Yeah.
Can I say negative cosecant square x?
If this is negative, this goes to plus.
So it doesn't matter.
There's a sign flip.
Yeah, right.
No negative, negative. If there's a negative, this goes to positive.
Okay.
There's a sign flip. That's the way to think about it. Is there a sign flip or not? Okay, here there's no sign flip. Here there is a sign flip. Okay, and by that, I'm not referring to the value of the expression. I'm saying whether or not there's that symbol there, that negative sign. Right.
Excuse me. I was just wondering. So if the negative for sine x, if we distribute it, the positive would become the plus c would become negative.
Yeah, I made that comment before. You might think it's more appropriate to have a minus c there, and that's fine. But by convention, we almost always write plus c. And the idea is that, look, negative 1 times an arbitrary constant is an arbitrary constant. We're going to see that in this chapter. That big C, we're going to treat him as like, he's a big blob. He's going to suck up constant factors that are right next to him, suck up constant terms. So basically, if you have C, and let's say that goes to 7c. We'll still write C. Let's say it goes C plus 6. We'll write C. So this guy here is going to suck up constant factors right next to him and suck up any other constant terms. Okay, and that doesn't affect this guy here. Okay. So in other words, if you see something like 7c plus 6, you can just make that a big C. Now you might argue, shouldn't that really be a D? Some people would argue that, make that a D. Yeah, but by convention we just say we can let C be a big blob. It's a big old arbitrary constant, and we don't require these to be equal. It's just a big old arbitrary constant. Although some people are sticklers, they write D. Yeah. Later on in 255, sometimes you have to make a distinction, but not now. All right. Let's go on. We have more. All right. What's the derivative of secant of x? This is self-referential. Okay, look over here. What's the derivative of cosecant x?
Negative cosecant x, cotangent x.
Yeah, you put the sign, you take cofunctions. Yeah. So it's negative cosecant x, cotangent x. Okay, especially here, some people like parentheses, but that's up to you. Right? Okay, therefore, the integral of, I'll write this as cosecant x, cotangent x, dx. I my dx is everywhere here, right? Dx, dx, right? Remember your dx is here. Remember, for form, right? Remember your dx is here. Remember your plus c's out here. Okay, I do take off for form. All right, so keep that in mind. Okay, we have a sign flip, right? So what's it going to be? It's going to be negative cosecant x plus c. Some people put the c in front. I don't care. All right. So there we go. Know these 6 cold. All right. Keep it up with these 6 flashcards. Know these 6 cold. Okay. Be prepared to invert them. Know how to invert them. Okay. Don't try to memorize these separately. I think that's a bad idea. Then you get really confused. Know the derivatives and then know how to invert them. Okay. Questions. It's always good to check. Okay. Remember, how can you check? Right? Take the derivative. This guy's derivative is that. This guy's derivative is that. This guy's derivative is that. Right? Okay. Always ask. How do you check? Make sure the derivative is the integrand. Right? If you do this right, the derivative of your answer should be the integrand. Okay. Questions. All right. I've mentioned repeatedly that this is kind of like inverting, except it's not one-to-one because of the plus c, right? It's not one-to-one, but it is like inverting, kind of like exponentials and logs, right? Okay, or cube roots and cubing. So how can we exploit those kinds of properties? All right, inverse properties.
Professor,
Yeah.
we were just talking about it, but like the plus c could be the constant that we just get rid of when we're trying to get the derivative of a function. Like usually you get like a function like x squared.
You're correct that when you check, for example, right, and you take a derivative, you're correct that any constant term will not have an impact on the derivative. You're correct.
Yeah, so that plus c could be that part of the function that we didn't take account for the derivative. Like the derivative of x squared plus 2 is 2x, and we just get rid of the plus 2. But then if we go antiderivative, the plus 2 could be is the plus c.
If I ask what's the integral of 2x dx, you must say x squared plus c. Okay. Bear in mind that that's a whole family of antiderivatives. That includes x squared plus 1, x squared plus 2, x squared plus pi, and so forth. Right. But you must give me the plus c. You must give me this for an indefinite interval. I must always emphasize that. Right. Anything else? All right. I'll do this by example. I'm not going to write the general rule. I'll do this by example. Right. The derivative of the integral of secant to the 4th x dx. All right. Now, you might be looking at this, and you might be going, well, I don't know whose derivative that is. By the way, the answer is not times squared x. Okay, it doesn't work that easily. That's a calc 2 problem. All right. But now, wait a minute. You don't have to work this out because, wait a minute. I have a guy. Okay, unless we're talking about where we have derivatives, so we're not at a VA or anything, right? Okay, but okay, so there are no VAs or anything, all right? So we have the integral. We have secant to the 4th x, all right? We take its integral. In principle, we're going to get some guy plus c. Then when we differentiate back, what should we get back? The integrand, yeah. So this basically indicates checking, right? What this inverse property is saying is it describes how checking works, which is that if you take the indefinite integral of something, in principle, you get a family of antiderivatives, okay? And then when you differentiate that, you better get the integrand back. So this basically establishes checking, right? Okay, so the answer here is just the integrand. So you don't have to know how to integrate that, right? It's like a trick question. You don't have to know how to integrate that, right? That's just the answer. All right. What if it goes the other way? The integral of the derivative of secant to the 4th x, okay? And all of this is dx. All right. We take a guy, we differentiate him. Now, actually, you could do this in principle, right? You should know how to differentiate him. and then you integrate back. You might not know how to integrate back though until later, right? What's our answer going to be? It's going to be secant to the 4x, but this time, since ultimately we have an integral, it's a plus c, because in the end you're integrating, right? But again, it's like an inverse idea, except that we lose the one-to-one property, so we still have a plus c. All right, just the idea that these operations essentially undo each other up to the plus c. All right. Differentiation and integration. Okay. In principle, that's a check also. You could check a derivative by taking its integral, but that's rarer. Usually it's harder to take an integral. See, here's the deal. Folks, if I throw you, except for like e to the x or ln x, if I throw you some like algebraic function or a fairly basic trig function, right? Even a more complicated trig function, or compositions, right? You should be able to take its derivative, right? I can give you some monster, you can take its derivative, and you can check it on Wolfram alpha or something, right? But if I give you a guy and I tell you to integrate it, in general, it's harder to integrate. You need more strategizing. Okay, and the process of integrating goes on in Calc 2. And there's some guys they won't learn how to integrate until Calc 3, if ever. So integration is harder. Okay, if I throw you some random guy, okay, it might be harder to integrate. Yeah. Maybe impossible. All right. Next. Okay, now it's so small here, but it's a very important principle. Okay, just like with the limit operator and differentiation operators, the integral operator is, what's that L word? Linear. What do I mean by that? Integration, indefinite integration, this is a linear operator. Okay, and polynomials, for example, love to hear that. Why? What does it mean to say that we have a linear operator? When you apply it to a polynomial, for example, you can integrate how by how, term by term, all right? So that means, what does that mean? It means that you can integrate term by term, and for any given term, if you have a constant factor, it basically pops out, right? Constant factors pop out. This should sound familiar, right? Because that's true for limits, if limits exist. I'm assuming these things exist, right? That's true for limits, that's true for derivatives, that's true for integrals. We can do things term by term, and then constant factors pop out. That's one reason why calculus, in some way, is easier than pre-calc, because that was not true for square roots, or sine and cosine, or logs, right? It is true for limits, derivatives, and integrals. You can do things term by term, constant factors pop out. Okay? Okay. That's one reason why, remember those cases here? I just erased them. If you have like a -1, right? If you have like a negative one, remember that first one? If you have a -1, it can pop out, right? A -1 factor can pop out, right? So that's yeah, all right. So some examples. Okay, we'll start with a polynomial. At this point, hey folks, if you believe in linearity, all right, like you believe in the Easter Bunny, if you believe in linearity, you should believe that at this point you can integrate any polynomial, right? You can integrate any polynomial. All right, example. Evaluate the following integral. Okay, evaluate, colon. I put the colon so that I don't have to rewrite this guy. Normally I have to rewrite him. Okay, the indefinite integral of, all right, and once again, if you integrate a guy with more than one term, if the integrand has more than one term, you should put grouping symbols. You must put grouping symbols. All right, so x to the 6th plus 3x to the 5th minus 2. Okay, we're integrating with respect to x. Okay, you must put the dx. Basically, if you forget things like dx, it gives me a rationale to not give you full credit, meaning like a -1, right? Okay, but okay, so we're integrating with respect to x. Okay, now I'll apply linearity here. Although normally you can skip this step. I mean, you know, linearity is second nature to you, so we normally skip this step. If you want to put it in, fine, but we normally go straight to the next one. But let's do it. Let's apply linearity. We can do things term by term. We have the integral of x to the 6th dx, right? Plus the integral of this dx, and the 3 pops out, right? 3 times the integral of x to the 5th dx, right? Because it's plus the integral of 3x to the 5th dx, the 3 can pop out, right? Okay. It can pop out of its term, okay? Don't put the 3 way out here, okay? Put it only for the term. Minus, the 2. I'll leave the 2 in there, minus the integral of 2 dx. I'll do this. All of the 2 can pop out, and the 1's left. And you don't even have to write the 1. Okay, so here I'm applying linearity. Again, I could have even popped out the 2. But again, you can skip this step if you give me this step. For a problem like this is easy. Answer only. I would take answer only for this. Now, I'm going to remove all the integral signs. I better remember to put 1 at the end. Plus c. You know what? You might want to do it right now. As soon as you remove all the integral signs, put a plus c. In fact, as soon as you see it's an indefinite integral problem, you may as well put a plus c at the very end.
So when you're taking the, doing it for each term, you're not plus c-ing each term at any of
Oh,
c at the end.
well, here's the idea. You're going to get a plus c1 from here, plus c2 from here, or plus c3 or minus c3 from there. Well, a sum or difference of arbitrary
Oh, I guess it
constants,
doesn't matter.
it absorbs everything.
Okay.
So c1, c2, c3, they all get
But
absorbed.
theoretically, you just like c.
Yeah, in theory, you could say c1, c2, plus c1, plus c2, plus minus c3. Bottom line, plus c. Okay, yeah. I was going to raise that point, yeah. Okay, so yeah, a big old plus c. So he'll absorb all the constant integration. Okay, he absorbs all that. Okay. All right, let's do some rules. Now, folks, again, know the difference. We're not differentiating. Don't say 6x to the 5th. We're integrating. How do you integrate? This is going to be x to the 7 over 7. And like Archie was saying, you could put plus c1, but if you do a plus c at the end, that takes care of all of it. You don't have to put a separate one for each one. Big old plus c at the end, that takes care of all the constant integration. All right, now, plus, I'll put a 3 here. Don't rush, okay? Integrate x to the 5th. That's going to be x to the 6 over 6, okay? Minus, for many people, this is the hardest one. Okay, I put the minus sign there. Whose derivative is 2? 2x. Okay, and it's x because that's dx, right? And that's a t, it's 2t. All right, 2x. Remember, you can always check by taking the derivative, right? Okay, let's clean this up. All right, and sometimes I accept various forms, as long as they're equivalent and essentially simplified, right? Okay, so equals, all right? We can leave that as x to the 7th over 7. Some people like 1/7 x to the 7th, all right? Plus, okay, this is going to be 1/2 x to the 6th, or you could write x to the 6th over 2. That's fine also. Minus 2x plus c. Some people like to make a single fraction. I say we're okay. I'm sure you agree that's okay. Okay, you could make a single fraction. All right, so 1/7 x to the 7 plus 1/2 x to the 6 minus 2x plus c. Don't forget your plus c. All right, let me emphasize that. Because come on, that's an easy point that you don't have to lose, right? Don't forget your plus c. Boxed in? All right. Once again, if you have time at the end of the test, how can you check that? Take the derivative. Okay, it's that inverse property. If you take the derivative of this, then you better get the integrand. Of course, the plus c is irrelevant. Derivative is 0. Okay, you can check. You can differentiate to check. Questions? Very mechanical, yeah.
The second step, where we split up the terms,
Linearity.
do they, do they put parentheses around them to separate them?
You can if you want. I mean, if it's easier on the eyes, you can do this. Okay, people normally don't do that, but if it's easier on your eyes, that's fine. There's nothing wrong with that. Like I said, you know, if you put on more grouping symbols and they're not wrong, you don't put them in bad places, I'm okay with that. I won't mark you wrong for that. Unless you put them in bad places. All right. Yeah.
So just as far as notation is concerned, that would be big F of x then?
Well, yeah, this whole thing would be like big f of x.
Okay.
And in fact, big f of x, it's any guy where you take any real value for c, that is a possibility for big f of x. Yeah, it's a whole family of possibilities, whole family of antiderivatives. Right. Okay. But you're right. By convention, big f of x normally corresponds to the antiderivative where c is 0. By convention, but it doesn't have to. All right. Question. So you go.
Is there like, because when we were doing derivatives, we had like the quotient rule and then the chain rule. Is that still?
Okay. Now, good point. Okay, now be very careful. You don't, just like with derivatives, you don't take integrals factor by factor, and you can't split them up. So we don't have super easy rules. Just like with derivatives, there were more complicated rules, right? Product rule, you had the pointer. Quotient rule, you had the song. Okay, but it wasn't just bang bang, right? Okay, same thing for integrals. Don't split up integrals that easily. He brings up a good point. Okay, you can break up easily for sums and differences. That's count 2. Okay, and you're not really taught a quotient rule, but you can kind of derive one from integration by parts. But the bottom line is the analog for a product rule is integration by parts. That's a procedure. You also brought up the chain rule. Guess what? That's the use of technique. That's the thing that confuses people in 5.2. That's after your chapter 4 test. Stick around after the chapter 4 test. I know you're maybe that's why people get confused, because I teach that stuff right after that exhausting chapter 4 test. But stick around after the chapter 4 test. 5.2 comes use subs. Basically, what do use subs do? The use sub technique allows you to integrate composite functions, right? And that's what the chain rule is. How you differentiate composite functions. And the use sub is proven by using the chain rule. So use subs are an integration, what the chain rule is a differentiation. And that's 5.2. But you have to learn the basic rules first. Yeah. So this will all be coming. Okay. Let's do this one, next one. All right, this one's algebraic, but he's still doable. All right, algebraic. The integral of, parentheses, the cube root of x squared. Okay, plus 4 over the square root of x dx. It's not as bad as it looks because, you know what? We can rewrite this. Remember, look at the thing. Think about it. Can you rewrite it in a nice way? Isn't that a lesson you learned in the chapter 3 homework?
Yes.
Right? See if you can rewrite it in a nice way. Like Paul was bringing up, we don't have a quotient rule right now, right? Or reciprocal rule yet, right? Okay, so rewrite this thing. That's pre-calc. We want to rewrite this so it looks more like a polynomial. All right? Integral. Okay, how can I rewrite this? Don't worry about the domain. What's the cube root of x squared? That's x to the 2/3. If you remember that, look back at my pre-calc notes, 0. Something. Pre-calc notes, right? X to the 2/3. 5. I think 0.5, right? X to 2/3. Plus, okay, 4 pops out. It's 4 times 1 over root x. What's 1 over root x? That's x to the negative 1/2. Negative because it's down there, half because it's a square root. All dx. You all agree with that? That's pre-calc. Okay. And my pre-calc people, you can see that. It sounds like you're my monkeys from Weird Law. My people, my people. You know how to convert like that. All right. All right. You know what? At this point, we're ready to actually integrate. We're going to remove the integral sign, remove the dx, put in what? Plus c. Yeah. When you remove the integral sign and the dx, you put plus c. So at any stage in this problem, I better see an equal sign, I guess, right? And either an integral sign and d something, or a plus c, if you've removed all that stuff. Careful. Integrate x to the 2/3. It's x to the, you can do side work here. What's 2/3 plus 3/3? 5/3. And you divide by 5/3. Be careful. A lot of you better not skip this step, okay? I know a lot of you want to flip immediately, but a lot of you benefit from writing this first, okay? Plus, be very careful. We tap out the 4. Okay. Integrate x to the negative 1/2. X to the, what's negative 1/2 plus 2x? Positive 1/2. Over 1/2. All right. Again, try not to do too much in your head. If anything, the A students get in trouble because they try to do too much in their head. All right. If you're dividing by 5/3, you're multiplying by what? 3/5. And bear in mind, I don't like compound fractions like that. I do want you to do that. Okay. 3/5. You can put the 3/5 out here. That's fine. Okay. Or just take out the 3. Okay. 3/5. All right. X to the 5/3. I have no preference for exponential form versus radical, so you don't have to put it in radical form. Unless it helps. Plus, be very careful, folks. 4 divided by 1/2. Is that 2? It's 8. Be careful. You might want to write it out. It's 4. In fact, maybe go over here, right? Side work. What's 4 over 1/2? It's 4 times 2. That's 8. Okay? Be careful. You might want to do another step. 8x to the 1/2 or the square root of x plus c. Again, you can differentiate to check. Some people might factor or whatever. I'm okay there. So 3/5 x to the 5/3 plus 8 times the square root of x, right? Plus c. All right. Questions? You know, do the homework. You do get good at this. Okay. So today's stuff shouldn't be too bad. Okay, we have 2 more examples, and then before I forget to tell you, once we get to can save differential equations for later. Yes. All right. Also, sorry. Okay, two more examples. This is 20 groups of calculus, right? All right. Example. This is t. Don't freak out. It's t. Integral of. Okay, root t, and then plus 2. That's all squared, all over t cubed dt. All right. By the way, I've gotten used to curling my t's. Why am I curling my t's? So they don't look like plus signs. Be careful. T's versus plus signs, 2's versus z's. That's a big issue in Calc 3. Because in Calc 3 you deal with z a lot. I cross my z's now. All right. Okay. By the way, and again, what Paul's mentioning, there's no quotient rule. At least not for now. There's no quotient rule. So don't try to do it like this. That's not the way to do it. Okay, there's no quotient rule. We want to break this thing up. It's algebra. This is really an exercise in algebra. Pre-calc. All right, for many people, it's the pre-calc part that's the hard part. All right, well, we're going to square this two-term guy. It's not technically a binomial, but it's a two-term guy, right? Okay, square root t. T, yeah. We assume there are no domain problems. Okay. All right. Square root t, we get t. Then you take twice the product. That's a two-way B term, right? Take twice the product. 4 root t, right? Plus 4 root t. Take twice the product. Plus 4 root t. That's the two-way B term, right? Plus square 2. You get what? 4. That all goes over t cubed dt. All right. So we're squaring that two-term guy up there. It's like squaring a binomial. Questions? Right? It's a squared plus 2ab plus b squared, basically, right? Okay, what do I do now? We break this guy up, right? We can split. Remember that we can split through the numerator like this. We could not split through the denominator. If this is flipped, then we're in bad shape. Okay, but, all right. Let's split this thing. Integral of, parentheses, I'm going to get a bunch of terms, t over t cubed plus 4. While we're at it, what is the square root of t? It's t to the 1/2 over t cubed, all right, plus 4 over t cubed, all dt. Any questions?
Could you pull the t out, do it a different way, where you just do t to the negative third times?
Well, you can do that. Yeah. You can make t to the negative 3 times all that. That's okay. That's equivalent.
Okay.
Right. By the way, folks, like he was mentioning, you can do that in here. Never pull variables outside of here. Only pull out constant factors. Never pull out variables. Okay, the variable of integration, you can never pull that guy out. So, I'm glad you folks ask these kinds of questions, so I remind myself of warnings. Never pull out the variable of integration. All right. That's okay. Okay, let's clean this up, simplify. Okay. Now this is 1 over t squared, but I'm more interested in this. We have t to the first over t to the third. Bottom line, that's t to the what? Yeah. When you divide powers of t, what do you do to the exponents? Subtract. What's 1 minus 3? Negative 2. Okay. Now that's the shortcut. See, I know you know that's 1 over t squared, but the way that we look at it, it's t to the negative 2. We prefer t to the negative 2. Now I know some of you are going, well, wait a minute. I thought that in final answers we didn't like negative exponents. Well, if you're doing the work, right, actually the power rule for integration prefers this form. Okay, maybe not as a final answer necessarily, but as part of our work. Right? So we prefer that to 1 over t squared. All right, t to the negative 2 plus 4t. Okay, well, this is side work, right? 1/2 minus, well, 3 to 6 halves, right? What's 1/2 minus 6 halves? Negative 5 halves, all right? Negative 5 halves. Okay, this divided by that is t to the negative 5 halves. Plus, pop out the 4. Okay, what's 1 over t cubed? T to the negative 3. And that's all dt. Kind of cram it in there. Cram in that dt there. Yeah, don't forget your dt. All right. Questions so far? Because this is prep. It looks like a polynomial. It's not, but it looks like a polynomial, right? We can remove the integral sign. I can kill the dt. I better put a what now? Plus c. Because when you kill these guys, you need to have that plus c there. All right. Careful. Integrate. Integrate t to the negative 2. T to the, add 1. Negative 1 over negative 1. I know it takes time to get used to it, but Yeah, you add 1. It feels weird because we're getting closer to 0, but you add 1. All right, add 1 and then divide by the copy. All right, plus 4 times, okay, t to the, all right, what's negative 5 halves plus 2 halves? Negative 3 halves. We divide by that, negative 3 halves. Again, be careful, take it step by step. I need more room here, so I'm going to erase all this stuff. Don't get the plus c, right? Plus 4, we're going to integrate t to the negative 3. That's t to the what? Negative 2 over negative 2. Any questions? We're applying linearity. We integrate term by term, and then constant factors pop out within each term. Within each term. Don't pull a 4 out of the whole thing. Okay? It's only when you get to each individual term that constant factors pop out. Okay, we just have to clean this up. Because remember, in the final answer, I might not want negative exponents. So to be safe, let's clean this up. Okay, this is going to be negative. T to the negative 1 is 1 over t, right? That's going to be negative, or the opposite of 1 over t. Okay, here, let's take a step here, all right? Plus 4. When you divide by negative 3 halves, you're multiplying by what? Negative 2/3. Okay? Not positive 2/3. We're not taking a perpendicular. Okay? That's just you flip it. Negative 2/3. Okay? Times 1 over t to the 3 halves. Right? Okay, so I'm incorporating that negative exponent. I'm going to go down here. Okay, what is, this does work, what is 4 divided by negative 2? That is negative 2. That does work. Okay, minus 2, okay, times 1 over t squared, all right, plus c. And then let's just clean this up a bit more. Okay, I do require you to do the arithmetic. All right, equals, so what do we have here? We have the opposite of 1 over t. Okay, some people like to put the c in front. Opposite of 1 over t. Okay, now this is 4 over 1 here, right? 4 over 1 times negative 2/3. We multiply across, that's what? Negative 8/3. Okay, so it's going to be negative 8 on top, 3 on bottom, and we have t to the 3 halves on the bottom. All right. And this is a case where it's safer to leave the 8/3 in here. Don't try to pull it out. Okay. If you pull it out, you get 1 over there. So this is probably safer. And then minus 2 over t squared, right? Minus 2 over t squared. And then finally what? Plus c. Okay, you can differentiate to check. It might be rather annoying. The check might be irritating, but you could check. Okay, opposite of 1 over t minus 8 over 3t to the 3 halves. In my notes, I wasn't as concerned about the negative exponents. But minus 8 over 3t to the 3 halves minus 2 over t squared plus c. Any questions? You get good at this. With practice, you do get good at this. Yeah, go ahead.
I remember at the end of pre-cal we did like the PDFs or.
Yeah, that's Calc 2.
Oh.
Yeah, if you integrate like a big rational guy, you use the partial fraction decomposition, integrate each piece. That's Calc 2. Oh yeah. Yeah, this is like genetics. A lot of the things you learn in pre-calc, you're going to see in Calc 2. Yeah, techniques of integration. Because it's hard to integrate. Okay, it's not as clean as differentiation.
Can we use substitutions or?
Well, we will in 5-2. That's the hard part. After your test next week, yeah. Yeah. Well, it's not really hard, it's confusing. It confuses people. We have, okay, good news, bad news. Good news, we have one more example. Bad news is trig. Trig. We get great trig functions. Okay, that's not bad news. Trig is fun, isn't it?
Yeah.
Integral cosine of x over 7 sine squared x dx. All right. All right. Okay, first of all, let's rewrite this thing. Okay, first off, you agree that 7 down there is really irritating, right? And we can factor out, but be careful. What do I factor out? It's not 7, it's 1/7. You factor out 1/7. Be very careful about that. Because a lot of people just take out like a big old 7. It's 1/7. Because 7 is a factor of the denominator. 1/7 times the integral of. Again, you can pop out constant factors, right? Again, constants are okay out here. You never pull out the x if that's the You never pull out the variable integration. All right. 1/7 integral. And then I'm going to rewrite this thing. All right. So here's one way you can rewrite this. Okay. I can break up that fraction. If someone were to ask you, what's a squared? Like, you know, a math 38 student asked you, what's a squared? What would you say? A times a. What's sine squared x? Well, we have sine of x times sine of x. All right. Okay. And then, cosine x goes, let's say here. One goes there. Or vice versa. Dx, over here, dx. Okay. Questions? Questions? Normally we don't require grouping symbols for a product, but if you want to, that's fine. All right. Okay, now, does this help us? All right, 1/7 integral. Hey, what is 1 over sine x? Cosecant x.
Oh.
Okay, cosecant x. Yeah. Well, now, let's cosine x over sine x. That's cotangent x dx. Now, on the back of your chapter 5 test, you might, or you know, for that matter, chapter 4 test, you might want to list those 6 basic trig derivatives. This should look awfully familiar.
Negative cosecant.
Yeah. Now, first of all, we're going to unravel the integral sign. Put a what? Put a plus c. Don't forget that. Because the thing is, you get so proud of getting this, you forget your plus c. All right, you have the 1/7. Okay. And, okay, right? Whose derivative is cosecant x, cotangent x? It's negative cosecant x, right? Because what's the rule? You might want to write this down. The derivative of cosecant x is opposite of cosecant x, cotangent x. Or maybe you mind dump that on part of your test, like the back, right? Remember, there's a sign flip. Okay. Now, some of you might be asking, well, shouldn't it be plus 1/7 c? You know what? The c gobbles that up, right? 1/7 of an arbitrary constant is an arbitrary constant. We don't worry about that. We just have the c absorb the 1/7. Okay, so don't worry about that. All right, we can pop this out. This is negative 1/7 cosecant of x all plus c. Some people put the c over here. All right, and you can differentiate your check. Question. Again, you can differentiate your check. Any questions? Nick?
Can we change the sine squared x to 1 minus cosine?
Oh, you mean down here?
Yeah.
Well, I mean, that is the correct identity, but I don't think that helps you as much here. Yeah, I mean, this is straightforward. It's very straightforward. Yeah, I don't think that, because remember, it's kind of hard to break up denominators like that. Although in Calc 2, you learn some distance. All right. So, well, if you're all caught up, you can get through 5.1 number 2 if you're all caught up. Wow.